Okay, let's jump into a deep dive on something that's absolutely fundamental, constantly shaping the world around us, but, well, often goes completely unnoticed. Water in the atmosphere.
It is easy to overlook, isn't it? We see clouds, feel the rain, but the sheer volume and dynamic nature of water moving through the air is, well, incredible. It's a key driver of our weather and climate systems.
It really is. We're talking about the air's moisture, existing in gaseous form as invisible water vapor, as tiny liquid droplets, or as delicate solid ice crystals.
Mm-hmm.
And there's this relentless vital exchange happening all the time, water cycling between the atmosphere, the vast oceans, and the varied land masses through processes like evaporation, plants breathing out moisture through transpiration, condensation forming clouds and dew, and finally precipitation bringing it back down.
That continuous loop, the water cycle, it powers so much of what we experience outdoors every day.
So using the source material we've got for this deep dive, our mission is to really untack the core processes at play, look at the different forms that water takes up there, and understand the patterns of where and how it shows up around the world.
Yeah, taking something completely familiar and seeing the complex dance happening just out of sight.
Exactly.
Let's maybe start with that invisible part, the water vapor in the air, which we usually talk about in terms of humidity.
Right. Humidity. It's just a way of quantifying how much water vapor is actually present. Our source material breaks this down into a couple of different ways to think about it.
Precisely. There's absolute humidity, which is the actual mass or amount of water vapor in a specific volume of air. You might measure it in grams per cubic meter, that sort of thing. It tells you the sheer quantity of water floating there.
And that quantity is going to vary a lot depending on location and conditions, I assume.
Oh, absolutely. It's a snapshot of the water content at one spot in time. But
Hmm.
often, a more useful measure is relative humidity. This is expressed as a percentage. It compares the amount of moisture currently in the air to the maximum amount the air could hold if it were completely saturated. Well, at that specific temperature.
So temperature is the key here because air's capacity to hold water vapor isn't fixed. That's the crucial bit.
That's the critical insight, yeah. Warm air can hold significantly more water vapor than cold air. Think of it like a sponge. A warm, expanded sponge can soak up more than a cold, compressed one.
Makes sense.
As air temperature rises, its capacity for moisture increases. As it cools, its capacity shrinks dramatically. This is why relative humidity is so dynamic. The amount of water might stay the same, but if the temperature drops, the air gets closer to its holding limit and the relative humidity percentage goes up.
So a desert afternoon might have a lower absolute humidity than, say, a humid jungle morning, but because the desert air is so hot, its relative humidity could be quite low, just because its capacity is huge.
Exactly, you've got it. The source notes that relative humidity is generally higher over oceans, which are the source of so much evaporation naturally, and lower over continents, especially away from coasts.
And when the air is holding as much moisture as it possibly can at that temperature,
Mm.
what's that called again?
That air is considered saturated air. It's reached its maximum capacity and cannot incorporate any more water vapor.
Got it. Saturated. And the specific temperature at which a parcel of air becomes saturated, if it cools down, is called the dew point.
That's right. The dew point is the threshold temperature. If the air cools to its dew point or below, any excess water vapor beyond its now reduced capacity will start to condense into liquid water or, ice.
Okay.
Understanding relative humidity in the dew point is crucial because it tells us the potential for that invisible vapor to turn into visible forms like clouds and precipitation. It also impacts our comfort. High relative humidity on a hot day makes it feel even hotter because sweat doesn't evaporate effectively.
Right, that sticky feeling. Okay, so we've seen how water exists in the air as vapor. Now, how does it perform that great exchange, changing state? Evaporation and condensation are the stars of that show.
They absolutely are the primary mechanisms for that phase change. Evaporation is the process where liquid water transforms into water vapor, a gas. The main energy source driving this is heat.
And there's energy involved in this change, right?
Yeah.
Even if the temperature doesn't seem to be rising.
Yes, that's the concept of latent heat of vaporization. This is the energy that water molecules absorb from their surroundings to break free from their liquid state and become vapor. It's stored as hidden heat within the water vapor itself, energy that was used for the phase change rather than increasing the temperature.
So what makes water evaporate more quickly? What conditions favor it?
Well, several factors increase the rate of evaporation. Higher temperatures are key, obviously, as they provide the necessary energy.
Hmm.
Lower moisture content already in the air means there's more room for vapor, so to speak. And significant air movement, or wind, is very effective. Wind constantly replaces the layer of air right next to the water surface, which might be getting saturated, with drier, unsaturated air, allowing more evaporation to occur continuously.
Okay, so heat energy turns liquid water into vapor and sends it up. Then the opposite process, condensation, brings it back down in a different form.
Exactly. Condensation is the process where water vapor transforms back into liquid water or ice. This transformation happens when the air loses heat and cools down.
Right.
As moist air cools, its capacity to hold vapor decreases. Once it cools to its dew point, it's holding more vapor than it can manage, and that excess condenses.
Does it just happen anywhere in the air, or does it need something to, like, cling on to?
That's a great point. For condensation to happen efficiently in the free air, it usually needs a surface. These surfaces are provided by tiny airborne particles called hygroscopic condensation nuclei.
Hygroscopic.
Yeah, these are microscopic bits of dust, smoke, salt from the ocean, spray things that have an affinity for water, and provide a surface for the vapor to condense onto.
I see.
Condensation can also occur if moist air comes into contact with a significantly colder object, or if the air cools down close to its dew point by mixing with colder air.
So cooling is the primary trigger for condensation. Is that the main thing?
Yes, a decrease in air temperature is the most favorable condition because it directly reduces the air's capacity to hold vapor, forcing the excess to condense. The amount of moisture, air pressure, and the volume of air also play a role, certainly, but cooling is the main driver.
It's fascinating to think about this constant invisible exchange, heat lifting water up as vapor, cooling air causing it to condense back out. Sort of a dance.
And that energy transfer is so important. The latent heat absorbed during evaporation is released during condensation. This energy release fuels atmospheric processes and is a critical part of storm formation, for example. Okay. So once condensation happens, the water vapor turns into visible forms. And what those forms are depends on the temperature and where the condensation takes place. Our sources list quite a few.
They do. The key distinction in the form often comes down to whether the temperature is above or below freezing when the condensation occurs, and whether it's happening directly on a surface or on those nuclei in the air.
Okay, let's look at the forms that happen when the temperature is above freezing point first.
That's where we get dew. Dew is tiny water droplets that form directly on cool, solid surfaces like blades of grass, leaves, car roofs, or stones. The water vapor in the air cools to its dew point upon contact with the colder surface and condenses right there.
So it's not falling from the sky?
No, exactly. Ideal conditions for dew are clear skies, calm air, high relative humidity, and cool, long nights that allow surfaces to radiate heat and cool below the air's dew point.
Okay, so dew isn't falling, it's forming in place on the surface. What about when the surface temperature is at or below freezing? That's when you get frost. It forms under the same ideal conditions as dew, clear, calm, humid night cooling surfaces. But because the surface temperature is at or below 0 degrees C, the freezing point, the water vapor skips the liquid phase and changes directly into minute ice crystals deposited on the cold surface.
So it goes straight from gas to solid.
Pretty much, yes. It's essentially the frozen version of dew.
I see the difference. Dew is liquid droplets. Frost is ice crystals, but both form on cold surfaces directly from vapor in the air. Now, what about when condensation happens on those tiny nuclei floating in the air, especially close to the ground?
Right, that's how we get fog and mist. These are essentially clouds that have formed with their base at or very near the ground. They happen when a mass of air cools rapidly enough to reach its dew point near the surface, causing condensation onto the dust particles and other nuclei floating in the air. The result is, well, reduced visibility.
Is there a real difference between fog and mist, or is it just a name people use?
Our source indicates there's a distinction, mainly related to density and how they form. Mist tends to have more moisture, with a thicker layer of condensed water around each nucleus, and often results in better visibility than dense fog. Mists are frequently found over mountains, often forming as warm, moist air is forced to rise and cools as it meets the colder mountain slopes. Fogs are described as drier, forming where warm, moist air masses move over colder surfaces like advection fog, or where different temperature air currents mix, causing cooling.
And smog is just the less pleasant, polluted version.
Exactly. Smog is simply fog mixed with smoke particles, which act as abundant condensation nuclei in urban or industrial areas. A bit grim, really.
Yeah. Okay, so those are forms of condensation near the ground or on surfaces. What happens when that condensation happens much higher up on those nuclei floating in the free air at considerable elevations?
That's where we get clouds. A cloud is a visible mass of minute water droplets or tiny ice crystals, or a mixture of both formed by the condensation or deposition of water vapor onto nuclei in the free air at a height above the ground.
And they look so different.
They take on an incredible variety of shapes and appearances depending on the height at which they form, their horizontal extent, density, and whether they're made of water or ice.
The source categorizes them based largely on height, which gives us a way to start identifying them, sort of.
Right. It's a useful framework.
Right.
We have the high clouds, typically found between, say, 8,000 and 12,000 meters. These are so cold they're primarily made of ice crystals. The main type here is cirrus, those thin, wispy, detached clouds that look like feathery brushstrokes across the blue sky.
Yeah, I know those.
Other types include cirrostratus and cirrocumulus.
The ones that often mean nice weather, or maybe a change is coming, right?
They are often associated with fair weather, yes, but sometimes presage a change. Next are the middle clouds, residing between roughly 4,000 and 7,000 meters. These are often a mix of water droplets and ice crystals.
Okay.
Common types include altostratus, which can form a featureless gray sheet, and alticumulus, which look like patches or layers of puffy rolls or waves, sometimes described as looking like sheep. The source also lists cumulus in this category, which can be a bit confusing as it develops vertically, but okay.
So puffier, but higher up than the low ones we often see.
Precisely. Then we have the low clouds, which can range from near the surface up to maybe 3,000 meters. These are mostly water droplets. Stratus clouds are low, layered, and can cover the entire sky in a dreary gray sheet, often bringing drizzle.
Ooh, stratus days.
Yeah. Nimbus clouds are the ones that scream rain. They are dense, dark gray to black, shapeless, and low-lying. Nimbus stratus is a classic rain cloud covering a wide area. Stratocumulus is also in this layer, like lumpy gray blankets.
Nimbus clouds are the ones you see and think, okay, time to head indoors. Or grab an umbrella at least.
Usually a good idea. Finally, we have clouds with extensive vertical development. This means they start low but can grow dramatically upwards through the middle and even into the high layers.
The big ones.
The big ones. These are the tall, puffy cumulus clouds we mentioned earlier that can build into towers, and the powerful cumulonimbus clouds. These are the thunderstorm clouds. Massive and often topped with a distinctive anvil shape formed by strong winds at high altitude pushing the ice crystals sideways.
It's remarkable to think that seeing my breath on a cold day, driving through a misty valley, or looking up at one of those giant anvil clouds are all just different forms of condensed water vapor happening under specific conditions of temperature and height. It's all related.
They are. Each form is a visible indicator of the invisible processes of cooling, condensation, and air movement happening in that part of the atmosphere.
So water vapor goes up, condenses into droplets or crystals, forming clouds or fog. What happens when those droplets or crystals get too big or heavy to stay floating up there?
That's when they return to Earth as precipitation. Precipitation is essentially the release of moisture from the condensed particles in the air when they've grown large enough that the resistance of the air can no longer support them against gravity. They fall out of the cloud and reach the surface.
And precipitation isn't just liquid rain, as you said. It can be solid, too.
Correct. The most common liquid form is rainfall, which is simply precipitation in the form of water droplets. When the air temperature from the cloud all the way down to the ground is below 0 degrees C, the precipitation falls as snowfall, which are aggregations of delicate hexagonal ice crystals. Beautiful, really.
They are. And what about sleet and hail? They seem similar, both frozen, but I know there are different forms of frozen precipitation. How does that work?
They definitely form differently. Sleet happens when precipitation starts as snow or rain falling from a cloud that's above freezing, but then it passes through a layer of air near the ground that is below freezing.
Okay, a cold layer near the ground.
Right. If it was rain, the droplets freeze into small, clear ice pellets before hitting the surface. If it was melting snow, it refreezes into ice pellets. It's essentially frozen rain or refrozen meltwater.
Okay, so sleet freezes on its way down through a cold layer near the ground. How is hail different then? Because hail can be huge sometimes.
Hail, or hailstones, are larger, solid lumps of ice. They form within strong thunderstorm clouds, those cumulonimbus clouds we mentioned. Raindrops or small ice pellets get caught in powerful updrafts inside the storm.
Lifted up.
Lifted up, repeatedly into extremely cold parts of the cloud, well below freezing. Each time they are lifted, they accumulate more layers of ice as supercooled water droplets freeze onto them. Eventually, gravity overcomes the updraft and they fall.
Ah, that explains the layers.
Exactly. That process creates those concentric layers you sometimes see if you cut a large hailstone in half. Hail occurrences tend to be more localized and intense than widespread sleet or snow, often associated with severe storms.
That distinction makes perfect sense. Sleet freezes, passing through a cold layer near the ground. Hail grows by cycling up and down within a turbulent storm cloud. Very different.
Exactly. So, knowing what precipitation is and its forms, it's also interesting to see the different mechanisms that cause the air to cool and condense enough to produce rain specifically.
Right. The source describes three main ways that rainfall happens, based on their origin.
Yes. First, convectional rain. This occurs when the ground and the air just above it are strongly heated, causing the air to become less dense and rise rapidly in powerful updrafts or convection currents.
Like bubbles rising.
A bit like that, yeah. As this air rises, it expands, cools, reaches its dew point, and forms tall cumulus clouds, which can quickly grow into rain-producing cumulonimbus clouds.
This is often the dramatic kind of rain, right? Like summer thunderstorms.
It can be. Convectional rainfall is often heavy and intense, but usually doesn't last for very long, and it's frequently accompanied by thunder and lightning. It's common in hot climates during the warmest parts of the day in summer, particularly prevalent in equatorial regions where heating is intense year-round and over large continental interiors. Think of it like the air boiling upwards in a way.
Okay, so heat driving air up equals convectional rain. What's the next type?
Orographic or relief rain. This happens when a moist air mass encounters a physical barrier like a mountain range. The air mass is forced to ascend the mountain slopes.
It has nowhere else to go.
Exactly. As it rises, it expands and cools due to the decrease in pressure at higher altitudes, leading to condensation and precipitation on the mountain's windward side, the side facing the wind.
And that mountain creates a rain shadow effect on the other side, the leeward side.
Precisely. The chief characteristic of orographic rain is that the windward side of the mountain receives significantly more precipitation. As the air descends the leeward side, it is compressed and warms up. This warming increases its capacity to hold moisture, reducing or eliminating condensation and resulting in much less rainfall, creating that dry area known as a rain shadow area. Imagine the mountain acting like a ramp that forces the moist air upwards.
Makes sense. And the third type listed?
The source briefly mentions cyclonic or frontal rain. It's noted as being associated with extratropical cyclones and involving the interaction and uplift of different temperature air masses along boundaries called fronts.
Ah, like warm fronts and cold fronts.
Exactly. While the details are referenced elsewhere, we understand it as a distinct mechanism driven by large-scale weather systems rather than just local heating or mountains forcing air up. It's like different teams of air masses meeting and forcing one over the other, leading to cooling and rain over larger areas.
It's fascinating that something as simple as rain can be triggered by such different processes, local heat, mountains, or vast air mass collisions. So given all these different ways rain forms, where does it actually fall around the world? I know it's not uniform at all.
Far from it. The amount of rainfall and when it occurs throughout the year varies dramatically across the globe. Our source provides some general patterns. First, rainfall generally decreases as you move from the equator towards the poles.
So the areas getting the most direct sunlight generally get the most rain.
Often, yes, due to the strong convection there. Also, coastal areas typically receive more rainfall than the deep interior of continents due to proximity to the ocean as a moisture source and coastal weather systems.
That makes sense. Closer to the water source.
Right. And speaking of the ocean, there's generally more rain falling over the oceans than on the land masses globally.
Are there East Coast, West Coast differences? I feel like I've heard that.
Yes, and it's tied to global wind patterns, the prevailing winds. Between roughly 35 degrees and 40 degrees north and south latitudes, you often see heavier rain on the eastern coasts of continents, with amounts decreasing westward. But further poleward, between, say, 45 degrees and 65 degrees north and south, where the prevailing winds are the westerlies blowing from west to east. The rainfall is received first on the western margins of continents and decreases eastward as the air travels inland and loses moisture.
And mountains running parallel to the coast must amplify that orographic effect we talked about, making the coast super wet and the other side really dry.
Absolutely. Wherever mountains run parallel to the coast, you'll see significantly greater rainfall on the windward coastal plain and mountain slopes, with a sharp drop-off in the rain shadow on the leeward side. Classic example.
The source also gives us a sense of the major precipitation zones based on the annual amount received, like broad categories.
Right. Areas receiving heavy rainfall, over 200 centimeters annually, include the equatorial belt due to intense convection, the windward slopes of mountains, and the cool temperate zones along western coasts influenced by moist ocean air and westerlies, and the coastal regions affected by monsoons, which bring seasonal heavy rain.
Okay, that's a lot of rain.
It is. Then areas getting moderate rainfall, between 100 and 200 centimeters, are common in interior continental regions and other coastal areas not in those heavy categories.
And the drier regions, where does it get less rainy?
Low rainfall, maybe 50 to 100 centimeters, is typical for the central parts of tropical land masses and the eastern and interior areas of temperate continents. Finally, very low rainfall, less than 50 centimeters per year, characterizes the rain shadow zones we discussed, the deep interiors of some continents far from moisture sources, and the high latitudes near the poles where cold temperatures severely limit the air's capacity to hold water vapor.
It paints a really vivid picture of just how varied our planet's water distribution is. Lush rainforests, vast deserts, temperate coasts, polar ice caps, all shaped fundamentally by these atmospheric water processes.
And it all connects back to the energy balance, air circulation patterns, geographical features like mountains, and the amount of moisture available, essentially the processes we've been discussing, convection, orographic lift, the movement of air masses, and proximity to the ocean. Some places, like the equatorial belt and parts of the western cool temperate zones, even have the benefit of rainfall spread relatively evenly throughout the year, which really supports dense vegetation.
Wow. We've covered a lot of ground, from the invisible vapor floating around us to the mechanics of how rain forms and the global patterns where it falls. It truly is an interconnected system driving the weather we live with every day.
It really is. These processes are constantly interacting, leading to the incredible diversity of atmospheric phenomena we observe. It's quite beautiful, actually.
This deep dive has been incredibly illuminating. Thank you for guiding us through the atmospheric water story. Really interesting stuff.
My pleasure. And as you reflect on these processes, the delicate balance of temperature, pressure, and moisture, maybe consider this. How sensitive are these fundamental atmospheric water dynamics, from evaporation rates to cloud formation temperatures and precipitation patterns? How sensitive are they to even small, ongoing shifts in global temperatures and atmospheric composition? What could even minor changes mean for the global patterns and weather events we've just discussed? Something to think about.
That's definitely a big question to ponder. Next time you look up at the sky, feel the humidity on your skin, or experience rain, maybe you'll have a whole new perspective on the complex, vital journey that water takes through our atmosphere.
Absolutely. Keep watching the sky and keep being curious.